Thank you, Kibok, for that introduction. And of course, I'd like to thank Park Systems for the collaborations we've had through the years. And of course, Richard and Deb and all the co-organizers for this meeting. So like what Kibok said, you know, my voice is a little hoarse as an understatement. I usually talk loud. And I have 150 slides, so I think I just got it to 50. Anyway, so I'm here to give you an overview of how we look at nanostructuring of interfaces and how we have used different types of assembly, manipulation, and of course imaging to observe phenomena at the nanoscale. So first, let me talk about Case Western Reserve University. We are located in Cleveland, Ohio. Nice summer day. It's usually like New York in terms of weather, but it's a very cultural part of Ohio. In fact, this is our building. We are next to the Cleveland Museum of Art and the Severance Hall, which is the home of the Cleveland Orchestra. And then nearby is Cleveland Clinic. So we have art, we have lake activities. We're near Lake Erie, and of course we have the Cleveland Orchestra. But several things you need to know about Case. And how many of you have seen this movie, Air Force One? Okay. So at the beginning of this movie, there's a scene where some of the paramilitary forces were coming in. Don't go to YouTube now, later. Okay. But that scene was actually taken at the rooftop of this building, the home of Cleveland Orchestra. And then there's another movie, Captain America: Winter Soldiers. How many of you have seen this movie? Okay. In fact, the producer and director of the Avengers series are graduates of Case Western Reserve University, the Russo brothers. So in the middle of that movie, again, you can look at YouTube later, they showed the headquarters of S.H.I.E.L.D. Okay. If you know S.H.I.E.L.D., then you know what I mean. That scene was taken inside the Cleveland Museum of Art. So it just tells you how big and how modern it is. And so sometimes we call this Case Western Reserve University, or sometimes it's the Hollywood of Ohio. Just kidding. So anyway, Case is, of course, established universities, more than 150 years. And through the years, a lot of Nobel Prize winners are associated with the university. The first American Nobel Prize winner is a professor at Case Western. His name is Michelson Morley. If you remember that experiment that was key to Albert Einstein's theory of relativity, that was first done at Case. And even the founder of Dow Chemicals, Henry Dow, is a graduate of Case Western. Now, we're also one of the first to establish a 3D printing institute. This is called the Think Box. In fact, I could be giving a talk today on 3D printing. Half of my group these days is involved in 3D printing. But one interesting thing here is that you can go to the campus and use it for free. That is, it's well endowed. So anyone can come there, establish an account, and use some of the facilities for free. This is my department. This is literally my office, and these are some of my current group members. So we do a lot of nanostructuring on surfaces, and what we do is we do chemistry at the interface, where we look at grafting of polymers or use of nanopatterning or different types of colloidal assembly to look at interfacial chemistry. I'm also the editor-in-chief of MRS Communications, and so I invite you to submit your best work, whether it's a short letter or a review article. Now, looking at polymers, we actually associate them with nanostructuring, the fact that you can tune the property of a polymer all the way to surface structuring on a flat substrate, you know, like a membrane, or all the way to a Pickering emulsion. So it's a very versatile nanomaterial, and comparable to how we would handle graphene, nanotube, silicon nanoparticles. Now, to do that, you need very good synthesis methodologies. And this is just giving you an overview that my background from chemistry, for example, allows us to take advantage of interfacial phenomena. So early on, we did a lot of work on polymers that are classified as electro-optical materials, including polymers that are photovoltaic applications, electrical conductivity, nonlinear optics. Then we delve on the synthesis of dendrimer nanoparticles. So these are hybrid systems where we look at energy transfer, charge transfer properties between an inorganic core and an organic polymer that has capabilities of emission, charge transfer, or electron transfer. More recently, we have been playing around with supramolecular assembly. So these are polymer templates that we can then graft a polymer or grow a polymer and come up with nuts. Okay, so nuts as in Boy Scouts or as in geometrical assemblies. In fact, the famous nut, you would say, is the Mobius strip, or a lot of geometrical shapes that can be done using synthesis. But today, with the time I have, I'm going to focus on maybe 4 or 5 projects. Let's see how the voice holds. And I'll demonstrate to you what we mean by nanostructuring and interfacial phenomena. So first, let me take you to the work we do on molecularly imprinted sensors. So when we look at a protein, we typically associate it with structural biology, but more importantly, it's an enzyme. So an enzyme has particular tasks. You can say it's a catalyst. You can say it's also a biomarker. But what it does is it does well by accommodating substrate. And through different types of kinetic behavior, you will have the corresponding transformation. Interestingly, the size of this is similar to that of a dendrimer. So we had this inspiration that if we can treat a molecular imprinting approach very much like a dendrimer, we can pretty much approximate the properties, if not the function of a catalyst or an enzyme. So as receptors and peptides, polypeptides, let's say you incorporate them in membrane proteins, then they act as ion channel regulators. In another sense, you want to look at them as a lock and key mechanism. So if you have a key, it can only open one door, or it can open several doors. It's a master key. But one thing, you need to associate a key and a lock. In terms of molecular imprinting, we have a key, but we don't have a lock. So how do you make a lock out of a key? You do this by templating. So if you have a key, a molecule, you surround it with monomers, and then by complexing it, you polymerize it or cross-link it. You'll end up with a cavity that is shape specific, but more importantly, non-covalent interacting specific. Therefore, when you remove the original template, you have a binding assay that is approximate of the original template. And you can do this kinetic study back and forth. So if you translate that to, let's say, a molecule, a chemical analyte, you basically have a cavity which is very specific, meaning you can have other molecules which will not have a specific interaction. So to do this, we took advantage of this molecular imprinting using electrochemistry. It's quite unique because electropolymerization is a very important tool to deposit it on electrode surfaces, or to do this chemistry on a surface plasmon resonance chip, which we do a lot, by the way. So in this case, you will deposit this film, do the molecular imprinting on a surface, and then use reflectivity or ATR experiments to sense the binding of the analyte. And we design monomers that are capable of interacting with the analyte, so you can have very good molecular imprinting on a surface. So one of the first papers we produce is to direct the template of drugs on surfaces using a polythiophene matrix. So the third thiophene monomer was used to complex with these analytes and electrodeposit them on a gold surface for doing SPR. What you can see here is theophylline, theobromine, caffeine, paracetamol, naproxen. I mean, a lot of you drank coffee this morning, right? So looking at caffeine, how do you know if it's caffeine versus theophylline or theobromine? They almost look the same. Okay. Of course, naproxen, paracetamol are analgesics. You know, if you have a slight fever, you take them. So this is easy, but this is hard. So what we effectively do is before we do this chemistry, we do some ab initio calculation. So these semi-empirical ab initio calculations allow us to look at the minimum energy of interaction between the analytes and the monomers. And then after we determine the ratio, 2 to 1, 3 to 1, we then electropolymerize this on the substrate. So these are the results of that first paper. So if we use naproxen as a template, the rest have very low response. If we use theophylline, the rest have very low response. In fact, if you go back to this scheme, theophylline looks very much like theobromine and caffeine. But if you look at the sensor response, the theobromine and the caffeine did not register a lot. And the same with paracetamol. So this is a very selective and even sensitive sensor. In fact, we've done it not only with SPR, but you can use QCM, you can use AFM, you can use electrochemical impedance spectroscopy, you can use fluorescence. And this is one paper we published using folic acid as a template on a quartz crystal microbalance. So the rest is history. We have tested for sarin. How many of you know sarin? Well, if you have sarin in this room, we'll all die. It's a nerve agent. Of course, I don't want to kill my students. We use a fake sarin. But this is the real sarin. The only difference is a methyl group versus a fluorine. Okay? Dopamine, okay? A common anticoagulant. TNT, all right? Again, I don't want dead students. So we use an analog, DNT, one less nitro group. Bisphenol A, melamine, morphine. I mean, we could develop something for fentanyl, I guess. And then aspartame. So this works well. Sensitive, selective, well-reported. And that means we can take this chemistry to any sensor surface. Now, let me take you to the next theme. We do a lot of polymer grafting. That is, we grow the polymer directly from the surface, okay? Another way to grow the polymer is you can graft this onto the surface, or you can polymerize through the surface. So we did a lot of chemistry development on the surface-initiated polymerization approach. In fact, we use various templates and different types of applications. Together with polymer brushes, we call them polymer brushes, we reported a lot of chemistry on polyelectrolyte electrostatic layer by layer deposition. Very simple. You do this experiment on 2 beakers, you dip your negatively charged polyelectrolyte to positively charged polyelectrolyte. You get nano layers easily, okay? Lots of undulation. And we've done that chemistry on flat surfaces and particle surfaces. So how did we combine the two techniques? Well, back in 2014, we were very interested in super hydrophobic surfaces. And of course, a number of you know the lotus effect. So if it's raining, you see these droplets falling from a lotus leaf, it's because it is super hydrophobic, okay? What it looks like is this. So by SEM, so it's a lot of hierarchy of roughness. And to get this into a non-wetting state, you basically take advantage of what we call the Cassie-Baxter approach, which is you trap air, and then you form a droplet because of the failure to form a continuous line tension. So if you try to do this, and many people have done, using lithography, non-lithography, we're actually doing 3D printing. We're 3D printing super hydrophobic surfaces these days, is we can also template them. So if we use a silicone mold, we basically put the silicone on top and then copy it. We take this copy and then we register it so that we can grow a polymer brush. The polymer brush here is not an ordinary polymer. It's what we call an LCST polymer, meaning you heat it up, it becomes hydrophobic. You cool it down, it becomes hydrophilic. So you take this chemistry on a patterned surface, and this is what you get. So this is the real lotus leaf. This is the fake lotus leaf. So everybody likes to read fake news. Why not fake materials? Okay? So imaging is very important. This was actually using IR because we want to see the constitution. In fact, a challenge to you, the AFM community, is to get more spectroscopy out of AFM, get more chemical information out of AFM. If you can do that, that will open a lot of features that are not reported before. And several companies have been trying to do that. So AFM plus spectroscopy is a very good marriage. So what we did is these artificial surfaces, we compared it with a flat surface, okay? So this is the lotus leaf replicated surface. This is a flat surface. If we heat it up, the flat surfaces doesn't increase much. In fact, it's very interesting because it's hydrophobic and then hydrophilic, but the difference is only 30. On the other hand, the lotus leaf, the fake lotus leaf we made, when you cool it down, it's super wetting. I mean, you don't see a contact angle. Completely wetting. And in a matter of 15 degrees Celsius, you shift it from a super wetting to a super hydrophobic. 150 degrees change. Moreover, you can do this back and forth, okay? So this type of lotus leaf is fake lotus leaf, but also a smart lotus leaf, okay? So what else did we do with this marriage? We made colloidal templates that are capable of folding or doing origami-like structures. What we did is we made a pattern. The pattern can be lifted up from the surface, but before you do that, you impregnate it with polyelectrolyte layers on the soft side and another aluminum layer on the hard side. So to make these origami folding particles, you need to have a soft and a hard layer. The soft layer is stimuli responsive. So the soft layer folds and makes the hard layer keep the shape. So we did this by using the organic oxygen ion etching. I mean, this is the pattern. We made a cross pattern by AFM. You can see here the resolution. Also by IR imaging, we know that we have a polymer in the pattern. So we made cross shapes. We observed the folding of the cross shape and simulated it. It works. It folds by itself. We make this rectangular shape. It folds to form a cylinder. And we made this tuning fork just to emphasize the aspect ratio. You can see this trying to fold first before the rest. So this type of artificial colloidal templates means you can do materials and lithography at the same time. Okay, how much time do I have, Richard? Okay, maybe we'll just do 4. All right. So electronanopatterning and macroinitiators. So one of the first chemistries that I developed as an assistant professor, this I'm like ages already, was to develop a conducting polymer thermoset. This was done by making polymers that when you electropolymerize them, they basically cross-link at the surface. At the same time, they are redox active. So for example, one of the first demonstrations we had was to make a device out of a polymer that when we cross-link can change the properties of a junction device like this LED, okay? So that means we can tune the redox property of this and then change the turn-on voltage. What we also did was to functionalize ITO. So indium tin oxide, if you have a smartphone LCD, you always have an ITO. It's a transparent electrode. It actually looks like this, very rough. But by growing a polymer brush, we can smoothen it. But more importantly, we can add different types of work function layers. So for example, if we cross-link PVK on ITO, not only does it change the surface morphologically, but it makes the device more efficient. So this is ITO on a junction performance, a bulk heterojunction system. So this is a solar cell using polythiophene and fullerene. Just by ITO, you have this performance. But once you add the brush, it becomes more efficient in converting light to current. And the performance is comparable to another famous whole transport layer, P.PSS. Okay? Moreover, we can pattern it. We can make micro dots, and then we can electrodeposit, let's say, a polymer like this. Okay? This is considered like a micro LED, a blue LED. Okay? So if you can do micro, you can do nano. So this is the case where we use an AFM, basically a current sensing AFM or conducting AFM, and then you have a substrate which is also conducting. So you apply that bias voltage, and apply application of the bias voltage using materials like this or PVK, we can start writing. So what happens is as you write, you're basically polymerizing, and at the same time joule heating. You're producing heat. So because of the glass transition of the polymer, it produces a feature, and at the same time, it cross-links it. It forms a thermoset. So we made patterns, we investigated the function of the current, the function of the distance, we made devices for memory applications, and so on. One of the projects that my students did is I asked them to pair with the synthesis of new polycarbazole. These are very good whole transport materials for a lot of junction devices. So Cheng Yu, my student, synthesized these new polymers, but she cannot do AFM. So what we did is we prepared films using the layer-by-layer approach. Basically, we alternate these polymers, and then we electropolymerize them. So we cross-link them through the carbazole units. And then I asked Gotchan, why don't you pattern it? Use AFM to make some nice patterns. So he did. He made lines, he studied the effect of height based on current, and then he made a lot of studies. Now, they like to work together. And then one night, when I was about to go home, he showed this to me. And I asked him, why did you make a heart? Well, he said, I like it. Well, we're supposed to do serious designs here, logic circuits there. He said, I like it. Okay. And then 2 weeks later, they came to my office and they said they want to get married. Okay. Moreover, that work, that particular work, was published as the cover page in Macromolecules. So there's a love story in my group. Okay. Remember that. If you see this, there's a love story behind that. Okay. So this is my last topic. So in addition to using templates of molecules, we use templates of colloids. These are basically latex particles. I mean, the same latex particle you'll find in paint, okay? So these paint particles, we basically make one layer, just one layer on a film. And then we electrodeposit a conducting polymer around it. So after depositing the conducting polymer, we basically dissolve the particles by THF. Okay? The result is you'll get patterns like this. So these patterns, depending on the current, depending on the amount of material deposit, depending on the concentration, we played around with many variables. You can get a honeycomb structure, full dome, half dome. You can even harvest the particles. You can basically shave the particles, and you get capsules. Okay? This demonstration, we use this monomer to polymerize around these colloidal particles. And after removing the colloid, you're left with these arrays. So these arrays are basically conducting polymers. How do we know? Well, we can do AFM, electrostatic AFM. On top of that, inside those holes, we can do a lot of chemistry. We can do a self-assembled monolayer of an initiator and then grow a polymer brush. So these are really two polymers, a conducting polymer and also the polymer brush. And then when we use conducting AFM, the green color represents that of your conducting polymer, and then the blue color represents that of the non-conducting polymer brush. We can do this type of patterning based on different chemistries. In this case, we change the monomer to a macro initiator. We can grow the polymer brush just like this. Instead of growing it inside, we grow it, and here you can see the macro initiators templated by polymerization, and then you grow the brush. So we did this on 3 types of polymerization: ATRP, raft, and metathesis polymerization. The result is we get brushes like this. Now, since the inside is still vacant, we can do a self-assembly of this ATRP initiator and then grow a polymer brush. So what you see here is basically 3 types of materials: 2 polymer brushes and 1 conducting polymer. And we've used it for membrane and ion channel type of applications. Now, more after that, we look at using the templating of a drug, basically in naproxen drug. Now, this drug is very interesting. It only works in one type of enantiomer. If you take the mirror image, it doesn't work, okay? So the technique we have, to make a long story short, is basically molecular imprinting on colloidal arrays. What happened is that we made the device more efficient, but also it's able to distinguish the two enantiomers, as shown here, very efficiently. Okay? So again, because of time, I will not be able to explain it, and I'll just finish this off. So more recently, we've been playing with cowpea mosaic virus. These are harmless viruses. Okay? I don't think I have this virus. Something else. But anyway, by TEM, it looks like this. So if you take this, which is charged, you then electrodeposit it on a pattern, which we made, and you get this. Okay? So these are basically viruses that surround those patterns, and what we found is we can make freestanding films. Now, these freestanding films are being used right now by my colleague Nicole Steinmetz for anti-cancer drug delivery. These are basically cluster bombs because you have a very high concentration of the delivery agent. Instead of depositing them singly, you have a very high efficiency of drug delivery because of this artificial construct. Okay, so I ran out of time. I won't show this anymore, unfortunately, okay? But I'll just go to my conclusion slide. So my conclusion is this. There's a lot of chemistry you can do at the interface, for sure. And if you try to use a conversion of function, you basically use a bottom-up approach to, from nanoscopic to macroscopic. Or you can do the design in reverse, meaning get inspiration, let's say, from a lotus leaf, and bring it or reduce it into practice at the nanoscopic level. Key to this are tools like AFM. So AFM, IR imaging, other tools that are surface sensitive helps us to characterize this phenomena. And then I failed to show you the methods we use for high throughput fabrications. But basically, that's it. I don't have much conclusion, but I'll be happy to answer any questions. Okay, so the typical bias voltage, we basically measure it in volts. It was amplified, so anywhere from 1 to 5 volts. So the higher the bias voltage, the more Joule heating we have. We found you get a more polymer that's raised on the surface. So two effects. One is the bias voltage allows us to do electropolymerization. The other is that it produces a lot of Joule heat, which helps in the patterning.
I assume there's a reason for designing material like that, but maybe I didn't pick up on it. I see the sort of self-cleaning window stuff and so on.
Correct. So the inspiration there is basically self-cleaning windows or smart surfaces that are stimuli responsive. So the main phenomena there is the Cassie-Baxter approach. And okay, I don't have to go back. But basically what you have are this hierarchy of roughness, and you have, during wetting, a lot of air trapped inside that cannot go or move somewhere. And then you have the surface tension defined by the tip of those protrusions. Oh, okay. So good question. So why you want, for example, if you want to use heat to basically remove adhered surfaces and refresh it or produce a clean surface after a heat cycle. The other uses for it actually is for de-icing. And a series of paper we publish, this type of smart surfaces are very good for regenerating anti-biofilm surfaces. Yeah.
So regarding the artificial biochemical receptacles, how do you ensure that you get a cavity and not a complete encapsulation?
So that's a very good question, by the way. We surveyed the literature. One of the problems of molecular imprinting is very poor template removal. What happens is during molecular imprinting, a lot of them are simply trapped in the surface, and when you remove them, they cannot go away. So what we emphasize is very thin surfaces, very thin films, anywhere from a few nanometers to not more than 50 nanometers. The other thing is the conducting polymer changes the swelling behavior of those cavities. So when we reduce them, they swell in the solvent, they grow bigger, and therefore release the molecule or the template faster. And then we oxidize them back, it contracts to the original size. So a key to that, and we have a patent on that, the key to that is manipulation during the preparation with a solvent and a bias voltage. So you can have very high efficiencies. I like that question. Yeah, very important. Okay. Yeah, thank you very much, and have a good day.